In this video, we're going to examine rules that extend our basic derivative rules for functions by allowing us to combine them in products and quotients. The two rules are called the product and quotient rules, and we're going to go through each one of them step by step. The product rule is what we apply when we're taking the derivative of the product of two elementary functions. And unfortunately, it's not as simple as just taking the derivative of each one separately and then multiplying when we're done. That doesn't give us the correct formula for the slopes of this combined function. Instead, we have this rule that comes from the definition being applied carefully, but it's easier to remember as a mnemonic. It's the derivative of the first function, so we have an f and a g. Let's call the f the first function. The derivative of the first function times the second, plus this first function by itself times the derivative of the second. So each function will be differentiated. In the first term, we take the derivative of the first function. In the second term, we take the derivative of the second function, but it also comes partnered with the original matching function without a derivative. Let's apply that down here to the function we're given. We have 4x squared e to the x, and here we have the product of two functions of x, and we also have a constant multiplier out front. Now, applying all of our rules, that constant multiplier is going to stay around. It's going to be 4 times the derivative of everything else on the inside. The easiest way to do that is to put a 4 and then a parentheses, and then do all the derivatives of the inside terms next. Looking at our formulas here, our first function, or what we call f of x, in the formula up here is our x squared. The second function, or the g of x in the formulas above, is e to the x. Now we can apply our product rule here and see how the derivatives work out. What's the derivative of the first function of the f? Well, the derivative of x squared is 2x, and then we multiply that by the second unchanged, which in this case here is e to the x. Then we add the first unchanged, the first function is x squared, and then here it's a little challenging to see what we've actually done because we're going to take the derivative of the second term, but the second term is an e to the x, and the derivative of e to the x is also e to the x. So it looks identical to the original function, but we can see the pattern of derivative of one function, and then the original here, and we can see the g of x in its original form and its derivative here. And that's how we apply the product rule. Later on, we'll take a look at the quotient rule, and it has a similar kind of feel to it, but it is more complicated. For those who are interested, you can actually get to this more complicated rule here by looking at a ratio or a quotient of two functions and rewriting it with a negative power. We could write this as f of x times g of x all to the -1, and then use the product rule, or the product rule and the chain rule, which we'll see in a second. That combination will also get you to this form here. Most people, when presented with a quotient, prefer to use the quotient rule. It just tends to give us the simpler form of the derivative when we're done. The typical way we talk about the quotient rule is to talk about the top function and the bottom function. When we use that nomenclature and then we look at the formula for the derivative, or the formula for the slopes of this ratio, then we see the derivative of the top times the bottom, unchanged. That's f prime times g, minus the top, unchanged, times the derivative of the bottom. That is the whole expression on the numerator here, and then we have all over the bottom squared. Frankly, when I'm doing quotient rule calculations, I actually rhyme off that mnemonic: derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. I'll actually say that in English. Here we just have the mathematical notation for that same idea. Let's move to the next page, where we'll see how we can apply both the product rule and quotient rule in other examples. In this problem, we have the derivative of x times ln of x, and so naming our functions, this would be our first function, this would be our second function, and this would be a product. So we'll use the product rule for it. The derivative of the first is the derivative of x, and that is simply the constant function 1, times the second. so times ln of x. Capturing that idea in the notation that we used before, we have the derivative of the first times the second, unchanged. Then we add, for the product rule, the first unchanged, so the x stays the same, and then we look at the ln x and take its derivative, which is 1 over x. So here we have the first function not changed at all, and then we have the derivative of the second term. We often get questions from students about whether you should simplify derivatives, and typically the answer is not unless you're going to do something specific with it later. What we usually say though is do try to simplify the obvious cancellations at least. 1 times something. It's much easier to read and understand if it's just simply written as ln of x. And when you have something where there's no advantage to not canceling, you might as well cancel that as well. X over x is going to equal simply 1. So this would be the preferred form. This is technically correct though. This is the derivative of this expression here. So this would be a perfectly correct answer to the question, what's the derivative of x ln x? Moving down to the second example, we identify this here as a quotient. And so we'll need the quotient rule. With that in mind, we're going to look at the top and the bottom. And there's a choice here. You could take this 5 multiplier and include it in the top if you liked. You can't include it in the bottom, that would change it into 1/5. But you can include it at the top, or you can treat it as a constant multiplier that's happening first. That's what we're going to do because it makes the overall calculation a little simpler, because we just have a single 5 out front of the entire expression. So we'll have a 5 out front because it's a constant multiplier of a function, and then we do the calculations for the derivative inside. So the derivative of the top is the first expression we need next. The derivative of x squared is 2x times the bottom, unchanged. Again, using our rules from before, the derivative of the top comes first, then we get the bottom. In the quotient rule, we subtract next, and then we have the top unchanged, so we have x squared. We have a ln x in the denominator. Remember, it doesn't matter that it happens to be in the denominator. We just take its derivative of ln x, 1 over x here, and just put it next to the original top. Top times the derivative of the bottom. Close brackets. And all over the original bottom, ln of x, all squared. Again, this would be a perfectly valid place to stop with the derivative calculations. Because there is some simple cancellation available to us, it's probably worth going one further step and saying this is 5 times 2x ln of x minus 1x on top, so just minus x, all over ln of x all squared. That's typically as far as we would go in simplifying a quotient rule. Here's another example, clearly a quotient rule application. Take a look, and if you want, try it on your own first, and then we'll go through it in a second. All right, so let's take the derivative of 10 to the x over x cubed. This time we won't go through the top and bottom in the notation, we'll simply say it out loud. But the top is 10 to the x. We take the derivative of the top first. And here you have to remember the rule for derivatives of e to the x is e to the x. The derivative of 10 to the x is 10 to the x, but there's a scaling factor because the base isn't the nice e. We get a multiplier of ln 10. All of this is the derivative of 10 to the x. And then we multiply by the bottom. Once we have that term complete, we subtract the top unchanged times the derivative of the bottom, which is 3x squared. And then we divide by the bottom all squared. Tidying that up just a little bit to make it look like expressions we've seen here. We see it looks pretty much like b. We have 10 to the x ln of 10 times x cubed minus 10 to the x times 3x squared, and x cubed, then all squared. We multiply the exponents. That's the rule for manipulating those, and we get x to the 6. And so b is a correct answer. It's also worth noting that d, if you look carefully at this, is actually equivalent to b. If you take a look at each of these terms separately and look at the x to the 6 dividing the x to the 3, we end up with x to the negative 3, 10 to the x ln 10. And when we have x squared over x to the 6, we end up with 3x to the negative 4. Now that is another way we can take the derivative. So this answer here is equally correct. You would typically arrive at this version of the calculation if you had taken the derivative in a slightly different way. Instead of writing it as 10 to the x divided by x cubed, you could have written it as 10 to the x times x to the negative third power. And then using the other rules of products and later on chain rule, we would have gotten this derivative here. So both of these forms are exactly equal to each other. They just look different on the surface, and you can arrive at both of them through straightforward derivative calculations. Either one is perfectly acceptable as an answer.